Are you starting? Are you what are you starting now?
We're really just doing revision.
Revision at the moment. Yes, that
Yeah.
is towards the end of year now. Yes.
Yeah, so I don't really have anything for specialists, but I do have physics.
Yeah. Okay. We can do some any revision of the subject.
Physics,
Have you started relativity, general relativity?
yeah,
Are you
we
starting now?
haven't finished our physics content.
Not yet. Okay. So we can discuss the physics today. Let's go to the white. Do you want to show me something, or can we go to whiteboard?
We can go to whiteboard.
Okay, go to whiteboard. So, what shall we discuss today?
I wanted to learn about the photoelectric effect because I wasn't
Yeah,
there.
again. Okay. Oh, you missed out this. Okay, just yes,
Mm-hmm.
yes. It's very important experiment, and that is let's share the board. Okay. Yeah, photoelectric. Yes, and so basically, at the beginning of 20th century, there are few experimental in physics remain unexplained. Okay,
Mm-hmm.
I will probably outline some of the two of them because they are relevant. Okay, one is black body radiation. Black. Oops, can't write it properly. Radiation. Another is photon electron effect. Okay, I write down this here. The photon electric effect. These two experiments are different but related. Okay,
Mm-hmm.
and in history, that is these are two persons solve these two experiment. This is unexplained. This is two experiment unexplained. So that is unexplained. Unexplained experiment at the turn of the century. Okay, experiment. Of course, another experiment is atomic absorption. So experiment. Okay, so these are two of them, one and two. All right, I put the three here. Three is atomic absorption spectra. So it's atomic atomic absorption spectra. Okay, we'll just go to the first one. The experimental result for the first one is like this. That is this is just black body radiation. Can you see? I just draw the diagram here. So this is vertical is intensity, and horizontal is wavelength, right?
Mm-hmm.
So that is the intensity. So they have the source. For example, if you get the object heated up, can you see? If the object getting heat up, you can see that they will change the color, right?
Mm-hmm.
When temperature change, so when temperature change, that the color will change from let's just draw a few of them. So if the temperature change, it changes the color. Okay, if you continue the heat up, they will change the color. They also change the color. Okay, if you just draw another two. So basically, if you change the color, so they probably became yellow colors. Yeah, just use the graph for you. What's wrong with my pen? Okay, and if you go higher, even they will probably change the color. If the temperature increase, okay, the temperature will get in even get a green, getting green, or even continue to do that, will give it blue. It's something surprise, okay? So that is how the temperature change. Just to cut the story short, when temperature increase, that is so this is the temperature increase, all right? The temperature increase. You will see the source of the object changes the color, right? Because nowadays, do you remember any picture of a blacksmith in old days?
Yes.
Yeah, blacksmith just help you to fix your tool, okay, made by metal, right? Especially for farmers, right? What do
Yeah.
they do? They just put in the stove to heat it up, right? When they get heat up, they become softer, so they can use a hammer to hit the object so that we can give you whatever shape you wanted to, right? So that is a radiation. They call it thermal radiation, right? Thermal radiation. So this time, we know the temperatures increase, but this time we just measure intensity as a function of wavelengths. You know the wavelengths now? Wavelengths in meters or in nanometers. So this is wavelengths right down here. So this is wavelengths, wavelengths. Okay, so normally we use nanometer. Okay, we use nanometer or meters. And so if I draw the diagram here, you will see when the temperature is not very hot, and you will get the dependence like this. Can you see? The temperature getting hot. When the temperature getting very hot, the change that temperature become like this. All right. And with the temperature getting even hotter, they getting like this. Can you see? That is just continuous. So that is and eventually getting very hot like this. Can you see? Okay. And that is how experimentally we can measure this intensity versus function. Okay. However, if no matter what theory you apply before in the 19th century, like electromagnetism, right? So people believe that this is due to they have the radiation. So that is in any case they have radiation. Can you see the radiation? So radiation is just electromagnetic wave, right? So in radiation in old days, they think, well, that is probably that is due to the radiated electromagnetic wave. Okay, that is what people thought. That it is a wave, okay, radiation. So therefore, they use you use electromagnetic theory. However, their theory is give you this one. So their theory give you this. Can you see? I can use the dash line here. The theory give you this kind of the description. The theory works well when the wavelength is long. However, when wavelength getting shorter, the theory is quite different from the experiment. Can you see? So this is a classical theory, or this is called classical theory. Classical means that we perhaps just put the name here. Do you know Maxwell? Have you heard of Maxwell?
I know the Maxwell-Boltzmann diagrams.
Oh, not that one. Probably we don't mention his name. You can we just if we just use this idea, if we use the electromagnetic wave, all right? And the theory, so this is use the electromagnetic theory. We cannot explain this experiment. That is one of the experiment remain unexplained. You see. And by the way, if you look at the wavelengths, so this will be this could be very close to a circle. So this part is a violet. Can you see? This violet, and these will be infrared. Can you see? That will be the infrared in terms of wavelengths. All right. So in other words, they have the horrible name for this failure in physics. It's called ultraviolet catastrophe. Have you heard of this term? Catastrophe.
Yes, I think so.
Yeah, that means the electromagnetic wave theory is totally wrong. Okay. or at least they cannot explain this experimental result. Now they came to the a hero. His name is Max Planck. You know Planck?
Mm-hmm.
So Planck said, well, I can fix this problem. So what he fixed, so this is a Planck theory. So this time I can draw this solid line, can you see? The Planck theory can perfectly explain the experimental result. Can you see that? So this is a Planck theory. So that's why that is the beginning of quantum mechanics. Okay? That is his idea used for quantum. He just assumed that he used the particle, they use a photon, so they got the photon energy. He introduced the photon energy, so photon. So basically they say, well, we're not, in this case, the radiation is not the electromagnetic wave, but Planck's theory is that it's not a wave, it's but a particle, it's a photon, you see? Like a particle, you see? So this is a particle. So that is why, that is the beginning of that's why Planck was considered as the father of quantum mechanics, particle. Okay.
Yeah.
Now, he actually given the name, you give the energy level. So that is very important. So for the photon, he said, well, there's not the wave come out from this hot material. It's a particle, can you see? He says the particle is moving, can you see? This particle moving at the speed of light, can you see? It's called a particle. And he even actually derived the formula for this one. Very simple, so simple. This is a Planck's photon energy formula. If you do you know the formula that in a wave that the speed were equal to lambda multiplied frequency? Do you know this formula? So if you substitute this formula to replace this f, then we can get another formula, which is fc divided by lambda. Can you see?
Yeah. So
that is a big deal. This is the first formula in quantum mechanics. Okay, that from then we're no longer treating the radiation as a wave, but as a particle now. Can you see? And if Einstein, after 5 years, nobody pay attention to, not many people pay attention to this new idea, except Einstein. Einstein was actually work out many ideas. So one of idea in the year of this publication is 1901. And then they came to Einstein. Einstein is, Planck is focused on the Planck body radiation, but Einstein is focused on the photoelectric effect. Okay, so that we just write is Einstein formula. So Einstein came up with ideas. He said, well, if the light is not necessarily the wave, so basically this is the background. So this wave is also considered as light. Can you see? And that is an important unification in the 19th century, because before that we studied optics separately from study electricity and magnetism. And after Maxwell, after this 19th century, we know that light is a part of the electromagnetic wave. So Einstein used this idea. So Einstein used this idea, say, well, if that is the case, maybe we can use this photon. Can you see? So he said, well, what happened to the photon electric effect? I will talk about more about experiment, but here I just draw a simple diagram to give you some idea. So what is the photon electric effect? If I draw this material, so this is a metal. Can you see the metal, right? And if you use the source of light, if you use the source of light, you can see this light source, all right? And this light source can be, you can change the frequency or wavelength, right? Once you fix that wavelength, according to this photon idea, and you will see that the photon will be moving at the speed of light, carry this amount of energy, can you see? Moving at the speed of light. So that is a photon. Oh, by the way, photon have many properties. Photon have no mass, you see? Photon mass equal to 0. And the velocity is always equal to c, you see? Anyway, that is some background about photon. So what happens is if you use a light source, and that is metal, so this is metal. And of course, in metal, they got electron, right? They got electron, they got, so the electron, for example, electron here, I just consider one electron. There are many electrons, I just draw a few of them, you see? So this is electron here. So this dot represents electron. But in the meantime, they also have they call the lattice, which is just nuclear, which is positively charged, can you see? So electron cannot move outside because they got this dot, the red color represents the positively nuclear of atom. So however, if the photon come in, collide with electron, can just consider this scenario. So if the photon will come in and band with this electron, can you see? So they got the band. So what happens is that electron will gain this energy.
Yeah.
That's the idea. With this energy, electron can fly, can escape. So basically, Einstein think, well, that is why the electron will jump out. Can you see? You can use the green color, maybe more realistic, the green color. So they say that the electron can jump out from the surface, all right? Because we just assume that if the energy of photon is sufficient, maybe that velocity after escape is still moving, right? So that is the velocity after the electron escape from the surface. Of course, if you have velocity, it must have some earth energy, all right?
Yeah.
That EK will equal to this is electron, so we can still use this formula, okay? You can use m. This is mass of electron multiplied velocity square, okay?
Yeah.
So this electron is called the photon electron. Can you see? It's called the photon electron. So the electrons is this electron, okay? Is generated by photon. It's called the photon electron. Okay. Of course, if you can, we can, then we talk about experiment, okay? If this is just one, if the single photon, if you have more photons, they will generate a lot of electron, you see?
Yeah.
If you can accumulate this electron somehow, then we can use ammeters, okay? Because this is charged particle. When the charged particle enters the conductor, we can measure the current, okay?
Yeah.
So the current will not be equal to 0. You will see the current. So in other words, photon can generate electricity. That is called the photoelectric effect. Okay. And I just give you the formula first. Einstein argued that according to energy conservation law, the energy of the photon, can you see HF? Oh, by the way, H is the Planck constant. Do you remember? So H is called the Planck constant. Well, that is the formula we need to use here. Okay, Planck constant. Okay, so this is energy of photon, okay? So as this energy will transform into the kinetic energy of electron. That's for sure, all right? However, they are not necessarily equal, okay? Because during this process, when electron absorb the energy from photon, they have escaped from the surface. During the process, they have overcome the resistance or attraction from nuclear, can you see? So these red color are all positive, can you see? They're positive. So because of attraction, then electron will be slowed down, all right? So some of this energy will be wasted or be spended. Can you see that?
Yeah.
And can we call this depending on the textbook? Can we use W? Okay. So this amount of work is called work function. So electron have to do work in order to escape. Okay, we use this W to represent what we call the work function. That's just a name. Okay, work function. Why do we call it a function? Because this amount of work done by electron varies from metal to metal, from different material. Okay. So this is Einstein's hypothesis. Okay. Einstein's idea here. All right. Very simple. And according to energy conservation, this equation must be equal. So that is Einstein's equation. EK plus W. So that is a theory of Einstein. So it's simple. You got Nobel Prize for this simple equation.
Yeah.
Right? So the opportunity is became much rare now. It's you can't just use a simple equation to get a Nobel Prize nowadays. You have then started a lot of math. So that is a theory. So I hope that will give you the introduction. So what is a photoelectric effect? Can you tell me?
It's when a photon knocks an electron loose
Out, yes,
from a piece of metal, and that electron will have velocity, so you can use it to like generate a current.
Yeah, they can move to another electrode. Yes, okay. So that
I was wondering how we get the work when we calculate it.
Yeah, that can either be measured or use Einstein's equation, because we can measure the photon energy, can we? We just measure the color or frequency. Can you see that? Good question. So even we don't know the work, we can measure the EK and the frequency of photon. So work can be solved.
How do we get EK if we don't have velocity?
Well, I will tell you, this is theory at the moment. If we next I will show you how to measure this EK. All right. If we assume that this both kinetic energy can be measured, and the work done, the work function can be simply written as this form. Do you agree? Now your question is, how do we measure the kinetic energy of electron? Is that right?
Yeah.
Yes, I will show you. that I will show you. But before we go to experimental part, we have to understand what is a photoelectric effect and how Einstein borrows idea from Planck to explain this phenomenon. Because you see, before Einstein, and both black body and photoelectrical effect was described by the old theory, like electromagnetic wave, right? But that's why both of them could not be explained, because Einstein learned that Planck explains the black body radiation. Einstein said, well, perhaps we can use this idea, the photon idea, to describe the photoelectric effect. And then he succeeds in a very short time. His theory is a simple theory, proven to be correct. And he got a Nobel Prize for this. All right, let's go to experimental part. All right. So to do this experiment, we use a vacuum, okay? Because the electron, you can hardly detect electron, because in air there are many atoms, okay? And that were defect. They were changed. They can block electron, or like at least slow down, okay? So let's talk about experimental part. So that is experimental part. Experiment. And to do that, you need to build the vacuum. You see vacuum? Can we use a vacuum like this? So can we this is a cylinder that is cross section, right? It's vacuum. Then when we put the metal, where should I put the metal? We put the metal here. Can you see? This is a piece of metal, not a very small piece. That's enough. And then we put the light source here. That is a diagram in your textbook. Can you see? We put the light source here. Here's the source. Can you see? So some of the so that is a pathway of photon. Can you see? We just at the beginning we don't know this photon. All right, we just pretend we don't know this photon. It's just the ray. You see the sun ray, the light ray. You see the light ray here, light ray, or the wave even. Okay, and the light wave is the intensity of light. Talking about we can talk about intensity again. So the intensity of light is very proportional to the so that is intensity. Can we call the light? There are a few ideas we need to discuss here. So one is light intensity. So light intensity. Light intensity, that is I, okay. And according to Maxwell's, according to electromagnetic wave theory, the light will be proportional to the strength of the field, okay, electromagnetic field, and that is so. Therefore, intensity is high. Oh, I want to keep that this place free, because I'm going to draw another part. Okay, we just assume this is light come from here. So electron were generated. Can you see? Can we draw this? This is electron. So this is one of electron. Can you see? So this is one of electron, and electron were generated with the initial velocity. Okay, so we just assume the electron once they come out, once they will generate that electron. Can we say this is velocity of electron, right? Now, how do we detect this electron? We can build this circuit, simple circuit. So what we do is we just connect this part, okay? And there are two experimental setup. So one is, can we just use this switch here, okay? And this time, we want to accelerate its electron. Okay, on the other side, we built this. This is another metal. It's called connector. Can you see? And then immediately we put ammeter here. Can you see? In order to measure electron, because electron is hard to detect. So therefore, first of all, we just use we built some electric field. Can we say this is positive and this is negative? Can you see? How do we do that? We just put a pattern in this fashion. Can you see? And we put this is a negative, is a positive. Can you see? It's a positive. Can you see that? And also we got this. Have you seen this called adjustable resistor? Can you see that? So in other words, we can adjust the potential difference or voltage between these two. Can you see that? That's the potential difference. Okay, now because the electron is negative, so there is a force. In this case, there is a force acting on electron. Do you agree? The force.
Yeah.
That is a force. This is a red color. So this force, can we say this is a force is equal? Can we use F for the force? Can you see F for the force? Now, can we work out the force? What is the force formula? So that is the force. What is the force formula in this case?
Frequency. No.
No, I'll probably use a capital letter. You get confused with. I probably use a F, capital F, to represent the force. Okay, so the force acting on electron. So F, what is F? The charge, right? The charge multiplies E, electric field. Can you see?
Yeah.
However, if we don't know the electric field, we can at least to work out the work done. Can you see? Work done by the electric field is equal to Q multiply the potential difference. Can you see that? So this is work done. So this is work done. This is different. Okay, this is work done by the electric field. That is work function. Okay, forget about the theory. We have just pretend we don't know theory. All right. So it's work done by the electric field. Okay, work done by the voltage. Okay, by the electric field. Electric field. Okay, so that is work done. So basically, we know that if this is the case, their kinetic energy, okay, another thing says the change in the kinetic energy of electron were equal to work done. Can you see? So therefore, the electron will speed up. You see, the speed. So no matter how slow the electron is, and after that, after this acceleration, and their kinetic energy will increase. So this experimental setup ensure, can we call this called a switch one? So this is switch one. Is closed. Can you see it's closed in this case? So in this case, every electron generated by the photon will be accumulated. Can you see that? So that is how we use this formula, which is a basic formula here. So that will give us so the change in the kinetic energy, which is increase, okay, will equal to the product of the, can we use the charge of electron? EV, all right? So let's do experiment. So if I just, by the way, the number of electrons were proportional to the current, you see? So the current will be proportional to the number of electrons accumulated, okay, collected, you see? So that is the current side. So if we just draw the diagram, if I just draw the diagram somewhere, draw the diagram here, this time we have applied the voltage above zero, can you see? So this is a voltage applied, and this is a current detected. Can you see that? And so you would expect that if the voltage is the current will increase. The current will increase. Can you see? And this is if you don't apply, you probably just obtain connect a fraction of the electron, right? For those electrons, they can fly to that direction because electron come out randomly. Okay, you have to consider that direction. Without applied voltage equal to zero, the current is relatively low. However, if you increase the voltage, the current will increase. Okay, but ultimately that will reach to the asymptotic value because the number of electrons generated is limited. Does that make sense? So that is if the intensity is fixed, because the intensity, I still have read the name here, intensity of light will determine how many electrons can be generated without, forget about Einstein's idea, okay? That is Planck's idea, right? Now, this is setup one. Another setup is that we change we change the polarity of the applied field. So this time we just go to the second setup. So this one, so this in this case, this voltage is larger than zero, right? Now, if I just change direction this time, and we just switch off the S1, this time I go to the next setup. This time I use the switch 2. Okay, now this time I change the polarity of battery. Can you see?
Mm-hmm.
Again, we just use adjustable resistors so that we can adjust the value, you see. So this time, if the switch 2 is on, so then we can measure out this side. So that voltage is less than 0. Now, in this case, this is not positive anymore. This has become negative. So that in this case, the force, if I just draw the force here, the force is no longer toward the right. But in this case, the force acting on the electron will be backward, can you see?
Mm-hmm.
So the energy will decrease. Do you agree? The energy will decrease. So that is the experimental result. So if you just change that increases of opposites code, and you will see the experiment shows that somehow the current will stop at a certain value. Can you see?
Mm-hmm.
This particular value is called Vs. Can you see? Negative Vs. So what is Vs? That's called the stopping voltage. Because that's not idea, sort of stopping voltage. Stopping voltage.
Mm-hmm.
ing voltage. Okay.
Mm-hmm.
Vs. Okay. So this is where we can cut off electron, even there's a presence of the radiation, the photon, not the light radiation. Light is on, can you see?
Mm-hmm.
That is because no matter how large the initial velocity is, if the stopping voltage is strong enough, we can always stop the electron. Can you imagine that? Can we consider this is the fastest, the electron, highest speed? Can you see?
Mm-hmm.
They were without this this time, we have to draw this time. In this case, in the second, using the second, when we change the polarity, the speed of electric stick is backward. Can you see? So therefore, their velocity will eventually decrease. Do you agree?
Mm-hmm.
And if that, if we just consider extreme case, if the electron just have that much of maximum for the electron has maximum initial velocity, will be rebound. Can you see?
Mm-hmm.
Just like that. So therefore, this so-called stopping voltage will correspond to the maximum kinetic energy. So they have a simple relation, E multiplied Vs will equal to the maximum kinetic energy of electron. Does that make sense?
Yeah.
Because any electron with less initial velocity will already be rebound on halfway. Can you see? Some electron probably just rebound like this, all right?
Mm-hmm.
However, for this electron have maximum, so the maximum value. I'll probably just use this simple idea. So that is experimental result, okay?
Mm-hmm.
The max value. So that is, in other words, we can measure. So in other words, we can measure the maximum kinetic energy by using this formula, right?
Mm-hmm.
So that is the experimental part. So these two formula is important. So this is that is a relation between stopping voltage and the maximum kinetic energy of photon electron. Okay, and of course this formula is generally also applied, and but we just mentioned that. So this is a change in the kinetic energy were equal to the change in kinetic energy were equal to the E multiplied voltage. Okay.
Mm-hmm.
Now this is just part of experiment. Now we change this changes the color. So if I change the color of or frequency of the light, something very strange will happen. Okay, if for the given metal, if the frequency decrease to some value, and the electron will completely disappear. No matter how, for example, this is this is can we just write this formula? So this is so in this case, the frequency is larger than certain value. Can you see? Can we say this called frequency C? Okay. However, if the frequency is larger than this value, we detect no current. Can you see? That's very strange. Can you see? Can you see this? This is almost like noise, right? In other words, there's no current can be detected if the frequency is less than. So in this case, in this scenario, the frequency is smaller than certain value frequency. In other words, for example, if you use purple colors, right? You can see this experiment, you can measure this current. It's due by accumulate electron, right? Or you can measure the stop voltage to measure the maximum kinetic energy. However, if you use red color instead, and this phenomena disappear completely, no matter how strong the intensity is. Can you see? So no matter what, how strong the intensity is. Can you follow me? Perhaps I can use this color. So that is a photoelectric effect. That's why it's hard to explain by using the old theory. So that is background of this experimental background. Because according to old theory, well, at least we will generate some electron by using this radiation, right? Or electromagnetic wave. And by using this first setup, we can accumulate every electron. We can collect every electron generated. Do you agree? But why? But why this is this current is dependent of the frequency or the wavelength? It remains unknown. So what people doing is that they just set up experiment, doing another experiment. Okay. Again, we just pretend we don't know Einstein's formula. All right. So what do they do this time? They just measure. Well, because there's frequency dependence. So they're instead they set up this another experimental observation. This is stopping voltage versus the frequency. So they just turn to another type of experiment. All right. And what they found is very interesting. They found that the dependence of the stop voltage. We know that stopping voltage is also proportional to the maximum kinetic energy of electron. Do you agree?
Yeah.
That's a maximum. That's maximum electron. So therefore, you can see that knowing that the stopping voltage, okay, but that must be stopping voltage must be done in the presence of photoelectric effect, right? So basically, they continue to do this measurement. They just measure this, have many data here. For example, for the given metal, so this is their experimental data. So basically, I just draw this data here. So this data here, can you see? I put white color. That just is, can you see? Can you see that? Can you see the linear dependence? Can you see that? Okay. So what does this mean? That they notice that the stopping voltage. So basically, if you use the best fit, can we use a straight line to fit this one? Can you see? Can you fit this straight line? Can you see that? So basically, what is from this experiment observation? They observe that the kinetic energy. Can you see? Because this is proportional. So this means that the kinetic energy is proportional to the frequency. That's interesting. And it is proportional to the frequency. And to be exact, if I use this as this is a frequency, do you remember that that critical frequency we call it frequency C, right? So if the frequency is less than this this value and the voltage, the photoelectric effect disappeared. Okay, So these photons is another idea is called they called I call the stopping. They call the cutoff frequency. They also call the threshold. Threshold frequency. That is another idea. Threshold frequency, or I simply call the cutoff frequency, the cutoff. So the phenomena disappear. They call the cutoff. Some textbook called cutoff frequency. Okay, I use this FC. Can you see? Now, stopping voltage, cutoff frequency is if together. Now, use your mathematical knowledge. Can you build the equation for this one, please? How can we write a mathematical equation to build this straight line?
The green straight line?
Yeah, green straight line.
Um,
It's linear, right? It's a linear equation. Yeah, you can write down here. I can give you some space. Yeah, you can write down here. Yeah, frequency multiply x. What is x? No, x-axis is frequency.
Oh, right.
Yeah. Frequency x is acting in this case. X-axis is f. Yeah, put a radian here. So what is c? How can we incorporate this x-intercept here? Yeah, that's intercept, right? Can we incorporate this c into our formula? Yeah, that's right. Can we use Vs equal to? This is a slope here. We use this slope, right? Frequency. So what can we put the frequency here as
plus FC.
So when that equal to 0, the frequency is equal to negative. Can you see? What is the C? It's FC is negative. See, it's negative. You see? FC, right? Is that right?
Yeah.
Is that correct? Or probably have to put a slope there. Do you have to put a slope there?
Yes, but since we don't have any numbers, I think it's fine to do.
This slope here, can we use different other than mass? Because the m represents the mass. Can we? So can we just use k or alpha? All right. Can we just use alpha? All right. Because otherwise get confused with mass. So basically, when that's equal to, so therefore c can be solved. C equal to what? C will equal to negative. Can you see? Negative FC and alpha. Can you see? Can you follow me?
Yeah.
C equal to negative FC. So therefore, they must have alpha over here. All right. Okay. So this is experimental formula. All right. So now let's compare with Einstein theory. So what does Einstein theory say? Do you remember? Go back. What Einstein theory say? This is Einstein theory. Can you see? Okay. Yes.
Yeah.
Can we rearrange this formula? Let's go to this part. Let's go to next part. So we have experimental theory says that the stopping voltage, which also equal to the you can also say this is can we just use this formula? Use the kinetic energy. Okay, we know it's maximum. Okay, I don't have to specify the maximum. We know the maximum. Can you see? Can we say the stopping voltage, if you just multiply the constant, it will equal to EK, right? So therefore, S will equal to EK divided by E, right? Okay. So according to our experimental data, we know that Vs is equal to is linear function, the gradients. Okay, the frequency take the frequency cutoff or cutoff frequency or threshold frequency, or you can say the critical frequency. Okay, then we compare the Einstein's idea. Okay, that is this is an experiment. Okay, that is an experiment. Experiment. And then we go to the Einstein theory. Einstein theory. Einstein theory. Or they can call Einstein's equation. Einstein equation. So do you remember the equation? So basically, Einstein equation says that the photon energy, can you see, can be written as the sum of kinetic energy plus the working function, right? Yeah. So if we just solve this kinetic energy, we just solve this kinetic energy. And oh, by the way, can we continue? Because there's only difference between this E. So we can argue that the kinetic energy can be equal to, can we call beta, just different coefficient. Can you see that? So that is from experiment. So according to Einstein, that became clear. Can you see? That will be equal to h multiply the frequency. And minus, can you see? Minus W. Now, if you compare with these two equations, so what conclusion can we draw from this kinetic energy from experiment? This is a formula by Einstein, derived by Einstein. Can we make some conclusion based on this by comparison these two equations? So what is beta? Yeah, beta is Planck constant. Yes. So what is beta Fc equal to W? Yes. Yeah. Okay. So in this way, Einstein gave the very simple but quantitative explanation for the photoelectric effect. Yeah. And of course, there are many related to problem solving. After I draw this diagram, probably you can pick up the question to see if you can solve the problem. So basically, if you draw this diagram, this time I use EK now, can you see? If I use EK, the kinetic energy, and this is a frequency. For the given particle, for the given material, metal, then we can there already exists this straight line, all right? The slope is always determined by the Planck constant. However, the cutoff frequencies vary. Can you see? Vary. Yeah. So we can probably draw several straight line here, apart from this one. Why don't we? We'll just draw several of them. So this is probably one, material one, and material two. Can you see? Material three. Oh, by the way, what is Y interception? So they just two of them. That's enough. So this is a metal one. This is a metal one. So what is Y interception? Metal one is metal two. Different metal. So what is this value? Can you tell me from this equation? So this is cutoff frequency, right? This cutoff frequency. This must have something to do with the work function, right? Yeah. So when F equal to 0, that is negative W, do you agree? Yeah. And remember, this work function varies from metal to metals, okay? So in other words, if I just use this color, we can see, for example, if for this color, if we can see the photoelectric for the metal one. However, because you see different color, well, can we just use a red color? Can you see? If I use a red color, this is a red color. Can you see? So this is this is red color. So this is red color, and this is a this is the red color, and this is higher is can we say this is a blue color? Can you see this frequency coming from blue color? Okay. Now the question: if I use a red color light source, can we see a photoelectric effect from metal 2? Red color. Just, can you see?
Yeah.
However, if we just keep using this right light source, can we see photoelectric effect from metal 1?
Pardon?
It just pretending we are doing experiment. Okay, we change the color of this light source. All right. If I just use the red color, we can just see the photoelectric effect from the metal 2. If we still use this red color light source, can we detect the photoelectric effect from the metal 1?
No.
Why not?
Because metal 1 requires more energy than metal 2.
That's right. The cutoff frequency is higher. Can you see? That's it. That's it. You can. Do you have textbook? You can pick up the question to see if you can solve this problem. I stop here. Anyway, that is a photoelectric effect.
Yeah.
If you any question?
No, not really. I think I get it.
You get it. Okay. So why don't you, after that, you just you pick up a few questions from your at the end of chapter to see if you can answer those questions. All right. Okay. Okay, I'll stop now. See you next time. And goodbye.
Okay, thank you. I'll see you on Friday.
Friday. Okay, goodbye.